Completely gone.
Yeah, it really is.
Spring constant.
Okay.
In other words, it's a stiffness constant for those, we talked about this before. We dealt with kinetic energy, the ski slope, the running into the giant spring. It's a stiffness constant. The larger the value, the harder it is to stretch or shrink a spring or any elastic material.
It's gotta be, oh, is this like an ideal spring?
Yes.
So then mass would be 0.
Oh, this is the mass that you attach onto the end.
Oh, okay, never mind.
The mass that is accelerating. All right, so with that at least eliminated, let me write down what we have now. We have negative K, A is equal to negative M A omega squared.
Can you take out A?
Yes, you can. Your conclusion that we can't get rid of A was wrong. The negative sign, I could,
That can cancel.
yeah, I could just multiply both sides by -1 to get rid of the negatives. Or divide by -1. So what I'm left with is the spring constant is equal to M omega squared. So omega is just the square root of K over M. So I can now start making predictions. So let's get rid of this stuff. Find a marker that works. So I have a spring here that hangs in some natural state. Let's say that it initially is 2 meters long, which is a huge spring, but
That's really long.
it's a nice integer. I then put a mass onto it. Put a 5 kilogram mass onto it, and so now the spring is stretched to 3 meters. Let's make it 2.5 just so that, just cause. This is a new equilibrium position. It's not like I put the mass on it and then let go and watch the thing bounce. I put the mass on it and I gently lower it until it hangs naturally. I know that the force that's exerted by the spring obeys Hooke's law, because of course it's ideal. If I look at the forces acting on the mass, I have weight acting down, and I have the spring force acting up. It's in equilibrium, so what's the acceleration?
0.
0.
So I have, well, let's make a positive, why not? So I have Fs minus W is equal to 0.
And there's nothing horizontal.
Say it again?
I said there's no horizontal forces.
Right,
It's not
right.
really-
Substitution, I have a formula for Fs. So Kx or delta x, whichever way you want to write it, is equal to mg. Different from what we had over there, because 1, I wasn't dealing with weight, although that's easily dealt with. And 2, that is not in equilibrium over there. But this is. Now, I didn't put in negative Kx, because the negative just tells me the direction, and I already identified the direction here. I know it's going that way.
So displacement would be 0.5, right? And then
Yep.
is
So-
equal to 5 times 9.8. Is this on Earth?
Yeah, that sounds good. So 5 times 9.8 divided by 0.5, and we end up with 98. 98 what?
Newton seconds?
Not momentum or impulse,
Newton meters?
not energy or torque.
Spring constant is
Newtons?
What are the units of the weight?
Grams?
Oh.
Try that one again. What are the units of the weight?
Kilograms per second squared.
Newtons.
Or sorry,
Yeah,
Newton.
Newton's a whole lot easier. Kilogram meters per second squared.
Yeah.
Excuse
So
me.
Newtons and the units of the change in position.
Meters.
So therefore the units of this are,
Newtons divided by meters.
yeah, Newtons per meter.
Yeah, Newton meters.
I was on the right track with Newton meters, but I just had it in the wrong spot.
The anti-ed disease where you I mean, per out of all of your units. All right.
Yeah,
So then I come over here and let's say it's the exact same spring. Moving the spring from vertical to horizontal, it's still the same spring. The spring constant is still the same. This mass doesn't have to be the same as I have over there, so let's go ahead and change it just because. So let's make this mass 3 kilograms. And so now I can predict this value of omega. I'll give a label to it in just a moment. So that would be the square root of 98 over 3. That's 98 newtons per meter divided by 3 kilograms. Five point six.
5.715.
All right, I'm gonna answer Den's question first, but the follow-up question I'm gonna have is, what are the units here?
why is x 0.5?
Like 2.5 minus?
Yes, this right here, technically there's a delta in front of it. I got lazy. This is how much the spring is stretched from its equilibrium position, so it's stretched 0.5 meters.
Is the, okay, back to.
All right, let me. Sorry, what's the masses?
Is it Newton, wait. Is it Newton per meters and then like dot product kilograms?
So Newton kilograms per meter,
No.
or Newton per meter kilogram?
Yeah.
It'd be,
I don't know.
wouldn't that just be meters per second squared?
It would, no. All right, so let's take it piece by piece. So we have the square root, you left that out, of newtons per kilogram meter.
The unit is gonna be square root.
Oh, it'll simplify.
Okay.
A newton is a kilogram meter per second squared, as established a moment ago, over a kilogram meter. Kilograms cancel, meters cancel. You're immediately left with 1 over second squared,
Square root.
which is 1 over seconds.
Yep, okay.
1 over seconds. Okay.
Inverse seconds.
Now, we are dealing with some sort, there is a rotation involved here, even though it's not readily apparent, but this would actually be radians per second.
Why?
The rotation of the spring.
All right,
Oh, yeah, that's, sorry.
not rotation of the spring, but if I took this mass here and I stretch it out and I let go, this thing's gonna oscillate back and forth
Right.
in a cosine pattern. So oscillate back and forth. If I mapped it first time, it starts here and then basically it'll oscillate back and forth as said.
Part of me wants to believe that it's radians because you had the omega, but you just chose omega, right? Like you could have chosen, when you were writing
Oh,
down.
I chose omega specifically because that's the letter that's usually used.
Okay, gotcha.
Your textbook, to me, makes it more complicated, but they probably thought they made it easier. So if I took a wheel here, rotating about its center, and right here I have a peg sticking out. I have a light source up above. If this wheel is rotating around at some angular speed, omega, angular speed, if we look at the shadow that's being cast down here, that shadow is moving back and forth, exactly the way the spring does. So that's the rotation involved here. We have this angular speed of this wheel with this peg sticking out, and the shadow is in simple harmonic motion. This omega right here is angular speed. This omega down here is angular frequency. Mathematically, there's no difference between them. Philosophically, angular frequency is dealing with a one-dimensional projection. Angular speed deals with something actually going around in a circle. But they have the exact same units, they have the exact same symbol. I've never seen a situation where there's any distinction between them. If you have this omega and that omega in the same equation, you can get rid of, potentially you can cancel them out. You can treat them identically. So that is the introduction to simple harmonic motion. From this, we can also, we'll have to wait till Friday, we can also start predicting how long it's gonna take the mass to go back and forth. We can actually test it with a real slinky and show that, lo and behold, it is not as far off as you might think.
Was this chapter 10? Is that?
No, this is 17? We skipped some chapters after 10.